Hello, good morning all. Uh, well, so, in this lecture, we will be discussing about the last topic of analog instrument, basically electromechanical instrument, and in fact, I briefly mentioned about the galvanometer part in previous lecture, which is nothing but a PMMC instrument. Hello, okay, am I audible to all?
Yes, sir, you're audible.
So we were discussing about the galvanometer in at the end of last lecture, where we saw that it is simply a PMMC instrument, just that it is sensitive to extremely low currents, and the way it is achieved is by removing the extra weight associated with the pointer, right? So instead of that, a mirror is mounted on the coil instead of the pointer as shown here, a mirror, and there is a lamp which um, directs a light beam towards the mirror, and the mirror reflects the beam of the light on a center scale, uh, zero scale, a 0 point of the scale, right here. So when there is no movement, when there is no current flowing through the coil, but as soon as the current flows, there is a movement of the coil similar to the PMMC instrument, and along with that, the mirror will also move, which is attached to the coil, and that mirror deflection will also deflect the light beam towards a non-zero position on the scale, right? So here in this case, the light beam behaves as a very long weightless pointer, and instead of the spring which we used to have uh, for bringing the pointer back, or let's say the coil back to the zero position, we use taut band suspension instead of the spring arrangement. And in the case of this, the scale is in microamperes usually, and either you can scale this as microampere because we are measuring current using this, or it can be simply and by knowing the current sensitivity, one can compute the current value. So it can either have two values, so whether we are using it as a voltmeter or current meter, uh, ammeter, we use sensitivity as per microampere or per microvolt. Okay, it's a simple procedure, and the one important thing one must remember in this case is that when the deflection occurs, the linear deflection, let's say, is x, so the angular deflection is theta p. Theta p is associated with the pointer deflection. It is double than the deflection of the coil. Okay, it is due to the arrangement which is there. So um, yeah, fine. So one can look at some examples associated with this. It is important from that perspective. So I will just note down here for your reference that theta p is twice the value of theta, and which is nothing but x by r. Okay, x by r. So in fact, all the moving coil instruments which are based on the PMMC principle can be characterized using a moving system equation, which is shown here. Now, which type of equation is this? Which type of instrument does it indicate? Which is a characteristic equation of which type of instrument? If you remember our discussion, when we are discussing about dynamic characteristic of instruments, uh, which equation does it represent? Instrument does it represent?
Instrument.
Which type? Sorry? Second
Order.
order. Okay, second order instrument. So in that case, it can be very clear that the response will look like this to our step input, isn't it? And we also must have seen somewhere, you must have seen that these PMS instruments do indicate such type of behavior. So it will take some time, although this time is very small, but it does represent this type of response. So in this case, the theta is the output, that is the angular deflection, and current is the input, right? The amount of current, and theta is the deflection. So in that case, the different system components which describe the behavior, or which basically on which parameters their response depends, are these values, that is moment of inertia, d is the damping constant, theta is the deflection in radians, and then k is the control constant, which is probably associated with the taut band suspension or the spring, and then there is displacement constant. We have already seen in the case of PMMC instruments that it is depending on the magnetic field, the current, the number of turns of the coil, and the diameter, that is this value, right? So this is, sorry, this is not I, this is L. Okay, so L is the length of the conductor, right? I is the in this case I is the current. Now for this type of instruments, you can simply find out the value of Z and omega n, which are nothing but the damping ratio and the natural frequency of oscillation, right? One can represent this and find the relationship between find the expression for Z and omega n depending on J, D, K, and G. Now let us you can take an example. Let's say you are given that the pointer length, this total length is r, let's say, which is given as 1 meter, which is quite long. Number of turns of the coil are 400, and the length and the diameter of the coil is 2 centimeters. The magnetic field is 200 millitesla, and the spring constant is given by 0.3 into 10⁻⁶. X is the displacement over the scale. So let's say the pointer moves by distance x equal to 100 mm. Then you are asked to calculate the displacement constant, that is capital G displacement constant, which is BLND. You can easily calculate it. All the quantities are given, and you can calculate the coil current. Current sensitivity also you are supposed to calculate. How will you calculate current sensitivity? Once you calculate the current, so how much is the deflection? 100 mm. 100 mm. So the unit of current sensitivity is mm per microampere, right? So you simply calculate using this deflection and the amount of current with which it is this much amount of deflection has occurred. Okay, so these are very simple example. You can expect it in your mid-sem or your quizzes. Now in the case of galvanometer, usually the eddy currents are generated by moving coil. Okay, so what are the eddy currents? So we know that once current carrying conductor moves within a magnetic field, then the voltage is generated in that, right? So this is the electromotive force, that is EMF, which is generated once a conductor moves through a magnetic field. Now that will oppose the cause of the movement. Now what is the cause of the movement? The current flowing through the coil. That's why these are known as eddy currents, and these coils are wound on a frame. That means say this is a kind of a frame. Is a frame over which this coil is wound like this. Okay. Now this frame is non-magnetic and non-conducting. So whatever eddy current is generated in the moving coil. So current levels, which current level? So I must say eddy current level are controlled by damping resistor, which is connected in series with the coil resistance. Remember these wires. So there will be two taps which will be coming through which will supply the current which is to be measured, right? But along with this you can represent it like this. There is a current flow through a resistance. So this is the coil resistance. Okay, this is a coil resistance, but along with this, there is a purposefully connected series resistance through which this will be sent. So this is known as damping resistance RD, and this is the coil resistance RC. Okay, so the current level, which is decided by which is associated with the coil movement with causing the eddy current, is basically controlled by the damping resistor and RC. Okay, now if you evaluate how much current will flow and how much torque that will be associated with the damping force. So remember, there are, if you remember our discussion on the PMMC, there is deflecting torque, there is damping torque, right? So these two, controlling torque and damping torque, right? These two will be there along with the deflecting torque. So once the system will come into at halt or in that equilibrium position, damping force will not be present. It will only be present when there is a movement of the coil, right? So during the movement of the coil, the voltage developed in the conductor is given by this expression, where B is the magnetic field, L is the length of the coil, and V is the velocity with which it is moving. So how do we calculate? It is a linear velocity. So the angular velocity is given by this d theta by dt, and d is the diameter of the coil. So if you look from top, this is d. Sorry, this is d. So d by 2, that is radius, into d theta by dt will be the velocity with which the coil is moving within the magnetic field. And how many number turns are there? N. And what is the length? L. Right. So N into L is total number of part of the coil which is moving in this region, and in this region also equal number will be there. So 2 into N into L, right? So the EMF which is developed is, if you substitute this expression for V here, then you will get BNLD into d theta by dt. But what is BNLD? Can someone tell? What is BNLD? This expression also appeared in the case of PMMC instrument. This is nothing but capital G, right? Displacement constant. So if you replace this BNLD with G, and the damping current which will flow, which is nothing but the eddy current, is this developed voltage divided by the total resistance. How much total resistance is there? Coil resistance plus a series connected resistance RD, right? So EMF divided by RD plus RC, and EMF, if you substitute the expression of EMF which we just derived in this place and replace BNLD with G, then we get this expression, right? Now remember, the torque associated with the damping current, the damping torque. So you don't confuse TD, which is associated with the deflecting torque. So deflecting torque is G into I. If you remember, I is the current which is being measured, G is the displacement constant, right? Similarly, the damping torque is governed by G into I, but in this case, I will be the damping current, not the deflecting current or the current which we are trying to measure. So this is G into ID. So ID is this. So G into G by R into d theta by dt. So this is the expression we get. Okay. So if you see, if you go back to your original equation of moving system, so you see this expression is associated with damping. So this is damping part. So this is a damping constant, right? So this damping constant turns out to be, what is the coefficient of this expression? D theta by dt, G square by R. So G square by R is the damping constant for any PMMC type instrument. Okay. Now I leave it to you to calculate the expression for damping constant in the case of critical damping. When do we say that the instrument is critically damped? Can someone tell? When do we say that the instrument, second order instrument, is critically damped? Which parameter decides this?
Damping constant equals 1.
Sorry?
Damping ratio is 1.
Damping ratio, that is Z, is 1, isn't it? So that's why I said, if you express this equation in terms of Z and omega n, then in the expression of Z, if you put 1, then the damping constant, please don't confuse this. This is damping ratio. Okay, this is damping constant. So this damping constant is given by this expression, which is function of the moment of inertia and the spring constant, right? Control constant. So in this case, these two expressions are important to understand. Okay. Now, galvanometer, as I mentioned, that it is extremely sensitive, and it is the full scale deflection might be even 10 microampere. That means when you supply 10 microampere, it will go from 0 to the last position, 10 to 100 microampere. So it is used specifically for very low current measurement. Where it is mainly useful, it is useful as a null detector. So if you remember, in the case of Wheatstone's bridge, so you connect, probably you must have seen this G. We connect the galvanometer across the two terminals here. Okay, so R, R, R. So in this situation, when all the resistance are equal, the potential across terminals A and B is 0, right? So there is no current which will flow through the galvanometer. But as soon as there is very small change in one of the resistors, that will generate a finite voltage, even though it is very small, but that will cause the current to flow through the galvanometer. So what is usually done is that you use this as a variable resistance, go on varying this resistance till the point that you will observe a zero deflection on the galvanometer. So in that case, you will know that VA is equal to VB, isn't it? So in this case of Wheatstone's bridge, galvanometer can be used as a null detector. That means no current that will flow. As soon as the delta is significantly large, the potential difference will be very high, and it will cause significant amount of current to flow through the galvanometer, right? So we need to avoid this because they are very sensitive. It may also damage the instrument. So it is mainly basically used for as a null detector. Okay. So with this we have finished our discussion on different type of deflecting type instruments. Now we look at how one can utilize this, considering either galvanometer or PMMC as our basic choice, PMMC instrument as basic choice, to design ammeters and voltmeters and ohmmeters with user defined ranges. Now, as I mentioned, the PMMC and galvanometer have the range till up to few milliampere or microamperes. Okay, but let's say you want to design an ammeter which can measure the current from 0 to, let's say, 500 milliampere. So in that case, one cannot use this PMMC because it will saturate. So we look at how they can be used to modify the instrument, the measurement range of the instrument. So first we'll discuss about ammeters, then we'll move on to voltmeter and ohmmeter. Okay. Now in this case, let us see that here we are going to represent this symbol M for meter. Meter in what we mean to say is the PMMC type of instrument. Okay, PMMC type of instrument. And symbolically, we know that there is a coil resistance and damping resistance and all, or everything together. We are going to represent it as a meter resistance. So this is meter resistance. In this case, how can we extend the measurement range? That means, let's say my instrument is basically able to measure 0 to 1 milliampere, but I want to extend it to 0 to, let's say, 100 milliamperes. So in that case, what will happen to the extra current of 99 milliampere? You cannot pass this much current, it will damage the instrument, right? So to bypass the extra 99 milliampere, when 100 milliampere is there, I want to show it as 1 milliampere. When 0 is there, I want to show it as 0. So that extra 99 milliampere is bypassed, see, is bypassed through the shunt resistance. Okay, shunt resistance, which has very low value, as you can see, less than 1 ohm, and symbolically it is represented like this. So let's say you are measuring the current I, which is very high value, and for example, let's say I is 100 milliampere maximum, and for this 100 milliampere I want to show it with a meter which has a range of 0 to 1 milliampere. So for 100 milliampere, only 1 milliampere I want to allow it to flow through the meter. The rest of the 99 milliampere will flow through the shunt resistance. So RS is shunt resistance. Okay. Now what is required is we need to design the shunt resistance appropriately, right? So the equation one can establish for the current to be measured and the meter current. When we say meter current, we are referring to full scale deflection current. Okay, we are referring to full scale deflection current. So if you, I hope you remember what is full scale deflection. That means the maximum amount of current it can indicate. That is meter current IM. So I is equal to IM plus IS. IS is the current flowing through the shunt resistor. Right? So let's take an example that will establish the design criteria for an ammeter using a given PMMC instrument. So here you can see that this meter and the shunt resistances are connected in parallel. So when IM is flowing through a meter with resistance RM, IS is flowing through the resistance with resistance, a resistor with resistance RS. So IM RM is equal to IS and RS into RS, IS into RS, because they are connected in parallel, right? And we also have this expression that um, I is equal to IM plus I. So we use these two to get an expression or relationship between the measured current and the meter current and the resistance of meter and shunt resistance. Right? Now, if you use this example that let's say you are given a meter which is having 0.1 milliampere as full scale deflection, right? And the meter resistance is 99 ohm, and the shunt resistance which you have connected across it in parallel is 1 ohm. So if you substitute these values here, what is the value of I that comes out? Substitute all the values. What will be the value? How much is I?
10 milliamps.
10 milliampere, right? So what you have just did here is that you are given a PMMC instrument which has a fixed value of RM as 99 ohm and full scale deflection of 0.1 milliampere. By connecting a resistance in parallel whose value is 1 ohm, you have extended the meter range from 0 to 10 milliampere instead of 0 to 0.1 milliampere. Okay. Now, uh, so let's say this is a scale. So from 0 to 10 milliampere. So how much is 0.5 full scale deflection? So remember, the actual meter has a range from 0 to 0.1 milliampere only. So half scale means 0.5 full scale deflection means 0.05 milliampere. So when Im is 0.05 milliampere, how much is I?
5.
0.5 full scale deflection. Similarly, you can calculate it for 0.2 full scale deflection. So what does it indicate is that by making this arrangement, the scale is remaining linear. There is no difference. The scale will remain linear. So you can see, you manufacture the same instrument, and depending on the requirement, you can simply put a resistance RS in parallel and extend the range as per your requirement, right? So the design criteria is choosing RS appropriately. For example, you are given the meter resistance, uh, meter current of 100 microampere full scale deflection, and meter resistance is 1 kilo ohm. Okay, so you are asked to calculate what is the value of RS that need to be connected in parallel if you want to extend the range to 100 milliampere. So if you want to extend the range to 100 milliampere, then your equation becomes 1 plus Rm by Rs is uh, I divided by Im, which is 100 milliampere divided by 100 microampere, which is 1000, right? Isn't it? So what is the value of Rs that comes out? What should be the value of Rs? Hmm? What should be the value of Rs? Approximately, you can tell.
1 ohm.
Right? 1 ohm. Similarly, if you want to extend it to 1 ampere, you can calculate the resistance again, right? So this is very simple arrangement one can make for using PMMC as emitter of user specified range. Now, one important point I need to mention here is about the resistance which will use for shunt resistance. Now remember, even your current carrying wires, the which you use for making connections, have finite resistances which may be of equivalent value to the shunt resistance. So it is very important that you choose the shunt resistance properly, and they are not your common resistances which you use in your 101 or 102 or other labs. So they are special resistors and which have 4 terminals. Okay, so they are known as 4 terminal resistors. So why 4 terminal? Because we have already studied resistances are always 2 terminal devices, isn't it? But this is a 4 terminal resistor which you use for this purpose. The reason being that it has 2 terminals known as voltage terminals and 2 terminals known as current terminals, and the meter will be connected to in parallel with at the voltage terminals. Okay, and the current which you are measuring, it will be in the circuit, it will be connected through current terminals. Okay, the reason being that remember all these meter calculations and extending the range from lower value to higher value uh, depends mainly on RS, right? RS. So if the RS is incorrect, the entire scale will be wrongly calibrated, right? So to maintain this RS constant throughout the operation, irrespective of value of the current which is flowing through the circuit. Remember, when the current flows through the circuit, these are conducting elements. There will be heating effect, which will cause the change in the resistance itself, isn't it? So if the change in resistance occurs, that is Rs tends towards Rs dash due to current flow of I and the heating effect, the entire calculation will go wrong. Right? So to avoid this, the contact resistances are maintained at current terminals, where even though there is change in resistance in these contacts due to the flow of current, the resistance at these nodes will not change. Okay, so the dimensions and all are made such that the material which is used are made such that the voltage terminal resistances will not change. So effectively, the resistance between these two terminals will be used as the fixed value of Rs, that is shunt resistance. So please remember this. In this case of shunt resistance, we use 4-terminal resistor instead of common 2-terminal resistances. So in the case of ammeter, we use a swamping resistance, which is having a near zero temperature coefficient. That means along with the temperature increase caused by current flow, the environmental temperature change will also change the coil resistance. If you remember, we have discussed that the coils are made up of metal wires, isn't it? So when there is a change in temperature, there will be change in RC value. Means this RC value. To compensate for that, swamping resistance is connected in series with the meter, and it is basically made up of special material called manganese and constantan, so which have near zero temperature coefficient. Means the resistance value of swamping resistor does not change with temperature significantly. Significantly, there will be change, but very small in comparison to coil resistance. So what happens is, let's say if I treat this as RSW, so the total meter resistance, remember this total resistance becomes Rs plus Rm. Okay, so even if Rm changes, with temperature, we made sure that making the choice of material, that RSW does not change significantly. If I treat this as same with Rm varying with temperature, the total value, the change in the total value is small. Okay, and that is how the temperature effect is compensated. So swamping resistance is usually greater than coil resistance, or in this case, if I, so this total is Rm, so I should write your Rm is RSW plus Rc, that is coil resistance. And when you are calculating the range here, okay, the Rm is no more only the meter current, meter resistance, that is coil resistance. It must include the contribution of swamping resistance as well. So must be taken into account while calculating Rs. One more important term associated with ammeter, which is expressed, is known as burden voltage. Now, how do you connect the ammeter in a circuit to measure current? So if I have this circuit, let's say R1, R2, I want to measure current flowing through this. How will you connect it?
Series.
In series, right? So let's see if I connect it this way. This is my meter. Now, what is the expectation from a meter? That any instrument, whatever we are using for measurement, it should not disturb the system. What does it mean? That if with the in the absence of meter, let's say if the current was I, in the presence of meter, let's say it changes to I dash. So I should be equal to I dash ideally, isn't it? It should be equal to I dash. However, it doesn't occur because the meter will have a finite resistance associated with that, which I can represent it like this. Let's say So the effective circuit becomes like this. There is meter resistance, then Rm, R1, and then R2. And what will it cause? It will actually cause the change in current from I to I dash, right? So this I dash into Rm is the voltage drop across the resistance, right? And it is known as burden voltage or ammeter voltage drop. And what should be the ideal value of burden voltage?
0.
0. So we want it to be very small, as small as possible. All right. So to avoid the loading effect due to the use of ammeters. Then let's say you want to give a flexibility to the user that that ranges can be chosen depending on the requirement. Okay. So in that case, what you need to do, we have just seen that for a given range, let's say 0 to 10 milliampere, you have one R value, 0 to 100 milliampere, you will have another value, and 0 to 1 milliampere, you will have another value of RS. So for each range, in fact, you must have seen, I don't know how many of you use multimeters. Multimeter comes up with a knob, okay, to choose the range of the values of current or voltage you want to measure. Like so, 0 to 5 volts or 0 to 20, like this. So for the voltmeter, and for the current also, you can have the choice depending on the knob. So in this example, the multi-range ammeter circuit is shown where several shunt resistances of different values. So these remain the same. This is the meter, and in parallel with this, depending on the choice of the user, different resistances are connected. So for each value of the shunt resistance, you will get a different range which the meter can measure. Of course, the calibration should be appropriately done of the given meter, and for each cases it should work fine. What we mean by that is, let's say I1, I2, I3, and I4 are the four values of current ranges. So for I1 you have calculated RS1, then I2 RS2, I3 RS3, and I4. So in each case, when I1 is flowing, when the rotary switch, this is single pole multiple throw switch, single pole multiple throw switch, when it is at position B, then Im should flow through this, and I1 minus Im should flow through RS1. Similarly, when you are putting the switch to C, then the current flowing through the meter should remain the same, Im. When I2 is the maximum current range, it measure, and I2 minus Im will be the current flowing through RS2, like this, right? It is as simple as the previous one, just that it is a design for multi-range. But the problem associated with this is that you see at the moment of choosing one range over the other, when I'm moving the switch, remember these are mechanical switches. So when you are doing that, there is a finite time gap between disconnecting point from the node B to connecting to node C, right? So if when the switch is in the middle position, let's say at given instant of time, what happens is that no shunt resistance is connected in parallel with the meter. So what will happen in that case is that the entire current which is flowing will go through the meter, right? Isn't it? So what will happen? I wanted the maximum current that need to flow through meter is Im, right? But by while changing the switch positions at a few instant of time, it will happen that all the current will flow because there is no bypass path which is available through the shunt resistance to take the extra current. So all will flow through the meter and the meter will get damaged. Okay. So to avoid this, to protect the meter from excessive current flow, instead of these simple switches, you use make before break switch. which has a quite long connection, quite long connector. So what does it do is, when it is switching from position B to C, in this case, uh, so you make the connection with C first, okay, when it is moving in this direction, but it is not losing the connection with B. It is still maintaining it. That's why it is known as make before break switch. So uh, when it makes the connection with C, at the same time it is having some connection with B, and it moves further and comes at this position, then it is completely disconnected with B. So uh, in the previous situation where the connector was hanging in between two terminals for some time, there is no such case arises in here. Okay, so either B is in the shunt resistance connected at terminal B is there, or shunt resistance connected at C is there, or in between the two shunt resistance in parallel combination will be there in between. Okay, so this is basically make sure that the meter does not take too much current, right, and get damaged. So the meter is protected from excessive current. Another way of protecting the instrument is, rather than using multiple resistances in parallel, you can either choose uh, this arrangement known as Arton shunt arrangement, where it also protects the meter, but in this case you can see that the resistance or the shunt resistances are connected in series. Multiple shunt resistances, each will give a different range. Choice of the position of the terminal will give different range. Now you can see that in this case, when the meter point the connector is in between two nodes B and C, there is no current that will flow through the meter. It is disconnected completely, right? So this will protect the meter from damage. It is just that the resistances which will be used as a shunt resistance are slightly different, because here they are indicated with RS1, RS2. The calculation of each is independent, but it is not the case here. For example, when the connector or the switch connector is at position B, what is the equivalent at B? What is equivalent shunt resistance? What is the value of resistance that is in parallel with the meter? It is R1 plus R2 plus R3, isn't it? This is a shunt resistance. I will name it as RS1. At position C, RS2 is R1 plus R2. But remember, in that case, R3 will come in series with RM. Okay, so the meter resistance you should take is effectively RM plus R3. Here I should say RM dash is RM. And at position D, third shunt resistance is equal to R1, and the meter resistance is effective meter resistance is Rm plus R2 plus R3. Right? It is quite clear from this. Now, for the given values of R1, R2, and R3, and the meter resistance of 1 kilo ohm, and we are given the meter which has the full scale deflection of 50 microampere. You are asked to calculate uh, the three ranges of the meter. Okay, so for simplicity, let's calculate it only for the position B. Okay, so when it is position B, the shunt resistance is R1 plus R2 plus R3. R1 Rm dash remains the meter effective meter resistance remains as the actual meter resistance Rm, and using this value of Rm and FSD, please calculate the value of current range for position B. So what is the value of R1 plus R2 plus R3? How much is that? It is 5 ohm, right? 5 ohm. So I am into 1 plus Rm by Rs1. Im is already given 50 microampere. 1 plus Rm is how much? 1 kilo ohm. Divided by Rs is 5 ohm. How much is this? Approximately you can calculate. How much it comes out? Anybody? Am I audible?
Yes.
Hello.
So
Hello.
10.05. So you are audible.
Yeah. So how much is the current value that comes out?
So 10.05 milli.
10 milliampere,
Yeah.
approximately.
Yeah, approximately 10.
Right. So you see, we have extended the range of the emitter from 50 microampere, 0 to 50 to 0 to 10 milliampere, right? In this arrangement. So I leave it to you to calculate it when you switch the position of uh, the the connector from B position to C position. In that case, your RS2 will be R1 plus R2, but remember Rm dash, which we'll use in the calculation here, will be Rm plus R3. Okay, please do that. Now, it doesn't matter much because Rm is so high, means in comparison to Rs, of course. Rm is 1000 ohm and R3 is how much? 4.5 ohm. So that will not make much difference, but it is important to calculate the actual range of the current. So I leave it to you, that part. So this part and this part. So we have seen that how one can easily design an emitter using the PMMC instrument. Now, similar idea can be extended to design a voltmeter. Remember, we are discussing current measurement for DC quantities. So we are now at the stage where we can discuss DC voltmeter. So we know that the deflection of the current with the pointer is proportional to the current, and the current, of course, we know is proportional to voltage across which it is connected. So one can scale the meter that can be used to measure the voltage. So we know that Im is the current flowing through resistance Rm, that is meter resistance. So Im into Rm will give me the voltage range which the meter can measure. And we have seen that this is of the scale of 50, like few microamperes or few milliamperes, and Rm is less than 1 kilo ohm most of the times. So the voltage range is also quite small, which it can measure. So similar to ammeter, one can extend the range of voltage measurement by now the if you draw the analogy with ammeter, in ammeter to extend the range we connected the resistance in parallel. In this case, the external resistance will be connected in series with the instrument, and in this case, there it was called as shunt resistance. In this case, it is called as multiplier resistance because it is multiplying the range of the voltage measurement. So here, this again is the equivalent circuit, is a meter, and it's associated with resistance Rm, and you connect a series resistance Rs, which is known as multiplier resistance. So if you calculate the total voltage drop across the entire arrangement becomes Im into Rs plus Rm, right? Isn't it? So it so you can extend the range. So you can see that what is Vm, the maximum voltage drop that can occur across the meter when maximum current is flowing through this. What is the maximum current that is allowed? 100 microampere. So Vm is 100 microampere into 1 kilo ohm, which is 100 millivolts, right? 100 millivolts, isn't it? So you want to extend the range. You want to measure the value from 0 to 50 volts. Okay, so you connect a series resistance here, right? So how will you calculate the value of series resistance? So we know that V is Im into Rs plus Im into Rm. This is known quantity. This I have defined as 50 volts. So Rs can be calculated as V minus Im Rm divided by Rs. Sorry, divided by Im, which is Rs is nothing but V divided by Im minus Rm, right? So this is 50 volts in this particular example. Im is 100 microampere minus Rm. Rm is given as 1 kilo ohm, right? So you can easily calculate the value of series resistance that will be required to be kept in series with the meter. And again, the quantity, the material with which the series resistance, multiple resistance is made is again a magnet or constant term, because we want it to be least sensitive to temperature variation, right? Now, usually voltmeters are expressed in terms of their sensitivity as the total resistance that is offered for full scale voltage. Okay, so please calculate the value of Rs for these values: 50 volts, 100 microampere, and Rm as 1 kilo ohm. What is the value of Rs that comes out? What is the value of Rs? Hmm? Hello? Hello?
Yes, sir, you are audible.
What is the value of Rs in this case?
0.5 mega ohm.
Mega ohm. Okay, so let us say it is 500 kilo ohms. Hmm? Now, this much resistance is offered by the voltmeter for the range 0 to 50 volts. So the voltmeter sensitivity total resistance per volt you want to calculate. So divide this 500 kilo ohm by 50, that will be 10 kilo ohm per volt is the voltage sensitivity associated with the voltmeter, which is usually specified by the manufacturer. Okay. Now, uh, when you use, if I draw the same circuit, instead of current, I want to measure the voltage. Measure the voltage. So what is the typical characteristic a voltmeter should satisfy? Ideally, voltmeter resistance will be how much? Infinite, right? So you see here, in that context, voltmeter sensitivity should be high or low? Voltmeter sensitivity should be high, right? Right? When voltmeter sensitivity is high, the resistance offered by the voltmeter will be high, right? So there will be lesser and lesser loading effect when you are measuring the voltage. Remember, sometimes even these values of R1 and R2, let's say this is 100 kilo ohm and this is 400 kilo ohm, right? So these values are comparable, isn't it? So effectively, the voltmeter will load the circuit, and you will not be able to measure the correct voltage. But if you know voltmeter sensitivity, let's say the manufacturer has already given, and remember it is expressed with in the with full scale voltage, not measured voltage. Okay, so maximum is 50 volts that it can measure. So that is a full scale voltage that is used in the calculation of voltmeter sensitivity. So if you know the voltmeter sensitivity, then you can calculate the total resistance, right? And if you know the total resistance of the voltmeter, even though the measurements are incorrect, you can compensate it by with the knowledge of resistance of the voltmeter. Okay, fine. So similar to your multi-range ammeter, where we used multiple shunt resistances in parallel, or in the case of Arton Arton arrangement, where they were connected in series, one can choose multiple resistances connected in series with the given meter to choose the range for voltage measurement. Okay, so several multiple resistances are there, and you use a rotary switch which can take different positions B, C, and D. Accordingly, R1, R2, or R3 will be in series, and you can use this. So there are two configurations that are possible. One is parallel, other is series connection. Okay, so in the case of parallel, we know that individual resistances can be calculated. So there will be three ranges: V1, V2, and V3. For each, you calculate R1, R2, and R3, and connect it in parallel, and use a rotary switch to choose one of them to choose the range V1, V2, or V3. Right. The other option one has is connecting the three resistances in series. Okay, so depending on the rotary switch position, either R1 plus R2 plus R3 is in series, or if it is in this position, then uh, R1 plus R2 will be in series, and when it is in this position, R1 will be in R1 will be in series with the meter. Okay, so do we have time now? Okay, so that so this has certain advantage over this. So we'll look at it with an example in the next class. Thank you.